So suppose you're standing at the beach, you're relaxing a bit, you're enjoying your well-deserved relaxation because you just finished a feature. And then somebody starts whispering in your ear, hey, you should get to the other side first. And you're like, why? I like it here. And then he says, look behind you. So you look behind you and you see this. The Egyptians are coming. That was the problem Moses was facing. So it's obvious what Moses needed. Moses needed a feature. He needs to get to the other side, and he needed to get there quickly. And as a nice to have, it would be nice to get rid of the Egyptians as well. So, and ultimately, he got his feature. So something happened, and he could cross the Red Sea. And maybe you're like, how is that possible? Oh, we don't know, but we have proof that invisible things can happen. But maybe you know Moses from this story, or maybe you know him from another story, the Ten Commandments. Now the interesting question is, what was easier for Moses? Getting across the Red Sea, or getting the people to follow the Ten Commandments? The Ten Commandments, like, thou shalt not steal. It sounds very simple, but still, we know from history that Moses did succeed in crossing the Red Sea, but he never succeeded, people never succeeded in following the Ten Commandments into completeness. So, how does that come? What's the difference? And the difference is that we have civil laws, religious laws, and laws of nature. And civil laws are like, thou shalt not steal. They are imperative, expressing something that should be done. But they also need enforcement. We humans tend to violate them. So we need police or some police system. We need a court. But on the other hand, there are the laws of nature. And the laws of nature, they look like this. This is one of Newton's laws. And the nice thing about the laws of nature is that they cannot be violated. They're just a formula which expresses the relation between some state. They capture these relationships. And maybe this metaphor so far sounds a bit weird, because I'm talking about the laws of nature and I'm talking about miracles. But actually, it's quite a nice analogy, because even if a miracle happens, after that, the laws of nature still work. So the water still flew back into the river once the miracle was done, so to speak. So, how is this all relevant? Well, my boss needed a feature too. And I work at a company called Mendix, and we built an application development studio. And in it you can draw pages, you can draw data models, those kind of things. So you can build entire applications completely visually. And that's used by consultancy firms all around the world to create software for banks and those kind of things. So this is what our data model editor look like. And so we have entities, the blue boxes, and we have associations between them. These are like cross tables. And so one very simple feature from this application is what I'm going to talk about today. And that's like that associations, you see one here. I shall zoom in a bit. Should be drawn from entity to entity. And here they are connected to the borders, but for simplicity, we will be talking about drawing them from center to center. And so the nice thing is that they move along when I drag an entity. So the interesting question is, how does that happen? Will it work this time? Oh, this seems to be really hard. I think I shouldn't leave my presentation anymore. Everybody, turn off your Wi-Fi. Okay, obviously computers aren't deterministic. So let's talk first about the model behind what you just saw. So I'm going to provide a very simple, not really realistic implementation of what we just saw. And so you can imagine there's a model of an entity and a model of an association between it. And entities have a name and they have attributes and they are drawn at a certain location. And there are associations and they just connect to entities. And that's all relevant information that is there. And then we can render those associations with a simple React component. But actually, it's not that simple. So first of all, there's this render method. And it draws an SVG path. And that path is calculated in a function. And actually, that function doesn't just depend on the association, but it needs the parent and the child properties of association. And from those parents and child, it needs the x and y coordinates to be able to calculate the center. So actually, we need a lot of data just to be able to draw this simple arrow. And moreover, we want this arrow to be correct even if the entities are moved around. So somehow we need to subscribe to the fact or react to the fact that this might change in the future. And I first started with a very simple event emitter-based implementation. So we see that the component is forced to update whenever something in the association changes. It reacts to the fact that notify changed is called on this association. So we extend it with some event emitter logic. And then the interesting part is then when we move an entity, we update its coordinates. That's pretty straightforward. But then, surprisingly enough, we have also to look at the associations and have notified that if they were connected to this entity, that they should be updated. So here we have a function that intends to move an entity, but most of its code is about dealing with associations. And that's a bit weird. And that's how essentially what started the fault behind MobX. So we should draw from center to center, and we have now made sure that if we move an entity, everything is still correct. But what if updates come in from the server? Then we might also need to notify the associations. Or what if the parent or the child properties are connected to other entities? Or what if the name changes? It might be, what does the name change have to do with these associations? Well, if the name becomes longer, then the box gets wider, and then the center moves to the right. So we have to deal with that fact. And initially, you might forget about it. And the same holds when attributes are added or when zoom level is changed. So you have to think about all these features, all these use cases you have, and make sure that under every circumstances, your drawing, your rendering is consistent. So then finally, you arrive at that point where everything is consistent. Yeah. So what actually happens is that when we do something with the entities or the associations on top, it bubbles all down to the bottom because those changes might influence the anchors, which might influence the SVG path, which in the end influences the component that is rendered. So we have a waterfall of things that need to be consistent. So and in the end, you probably get this right, and then you're relaxing, and you're yay, and then you're there at sea, relaxing. But then, of course, you'll know what happens next. The boss needs another feature. And he used the application and he's like, it's nice, but you know what happens? If we have two associations between the same entities, you can only see one because they are drawn at the same coordinates. That's very annoying, so you have to do something about it. So you have to make sure it is drawn like this. And we're like, oh no, that changes everything. It's like the Egyptians are storming at us. I'll be wondering, how does that change a lot? I mean, it's just drawing a bit differently. So let's take a look again at our simplistic version of drawing these arrows. So what we need to do is when we draw an arrow, we need to find out how many similar associations are there in the model. And if we know how many of them are there and what our relative position is, then we can adjust the coordinates of this association a bit up or down so that it's drawn at the correct place. The problem with this is that now suddenly our calculation function doesn't not only depend on the association and the entities that are connected to it and their coordinates, but also to all the other associations in the model. Because one of the other associations might change, might connect to the same entities as the association we are currently rendering, and then we have to deal with that as well. So you can imagine that we already had an add association function, which just pushed a new association on our collection and rendered it. And now that function has to be extended, because from now on, it might be the case that if a new association is introduced, you have to move a bit to the side. So I can demonstrate that. So now there's a second association here, and the association that was first straight is now curved a little. So it has taken into account that there are now two similar associations in our model. Oh, I'm just making the same mistake again. Yes. Wow, miracles do happen. So, some observations from what we just did. First of all, we extended our rendering algorithm, the algorithm that calculated our coordinates. And secondly, we updated some quite unrelated to the feature existing other features, like adding associations, to make sure that with the new features, our rendering is still consistent under all circumstances. So we had to deal with essential complexity, namely a more complex algorithm, but we also had to deal with some accidental complexity. The fact there's another feature out there that might influence or might break our rendering. So the second observation is that basically if you have more features, you have more potential consistency issues. So it means that you have to police your actions more. We have to guard everywhere. Could this violate the consistency of my application? So that means that if there are more potential consistency issues, your actions will become more and more complex whenever you add a new feature. Or in other words, whenever you have more feature, each new feature to add will be more expensive relatively to the previous one, as is shown in this very scientific graph. So how can we cross this sea of misery? So one thing we can do is we make our actions more predictable. We make sure that they can be tested better, that they are separated better. So for example, we could divide them into separate reducers. And we have a reducer for entities, which deals with moving entities, and we have a reducer for our associations, and it also now knows how to deal with moving entities. So at least we now nicely separated those two pieces of logic, and we made it better testable and better predictable. But still, we didn't address the real problem, because the real problem is still in there. When we have associations, we need to think about what needs to happen when we move an entity. So whenever we add more actions, more logic, more functions to entities, we have to remind ourselves, how could this affect our associations? Do we need additional reducers for that? So I think in the long term, a better solution is making consistency violations impossible. Because if it's impossible to make your rendering inconsistent, then you don't have to think about how features affect each other anymore. Now this might sound a bit far-fetched, a bit ideal, but actually it is quite doable. So what we need to do is that we need to move from civil laws where we say they should be rendered from center to center in all circumstances, and then you start policing what are all the possible circumstances and how do I deal with them. And we should move from there to writing laws of nature, writing formulas, writing functions that are just kept consistent by the nature of your application. So you don't have to deal about that anymore. So how can we do that? And the funny observation is, and it maybe sounds very stupid, but in order to be inconsistent, you require redundant data. You cannot have inconsistent data if there's no redundancy in there. So if the anchors aren't stored on our associations, they cannot be inconsistent with our entities. The problem is that our rendering itself, the DOM, is actually a piece of completely redundant information of our state. So we need the coordinates in the rendering of our association, because we need to be able to draw it in the DOM. But that fact that there's some styling there describing coordinates, that is already redundant information, because we have that data already in our state. It's just duplication information into the DOM. And how we can rid of that is by splitting the C of our state. So what we really have to do is find the minimal state that expresses everything that lives in our application, and then derive all the other things from it. And what's very important is that you should try to avoid turning state into more state. So you have a piece of data, and then you, for example, reduce it, or you calculate some new data from it, and then you store it somewhere, in memory or in the DOM, because as soon as you do that, then you have to keep it consistent. Still following this? So from a consistency waterfall, we should move to a place where everything that is derivable is derived. So only entity and associations express a state that lives in our application. And the rest can all be derived from that. So it can be expressed in a formula, in a law of nature, and then we need nature to keep it in sync. Of course, you need some nature for that, something that implements your laws of physics. That's where MobX comes into play. That is what MobX does for you. And MobX basically has only 4 concepts. It has observable values. This is your state. So these are the values your app is really about. And then there are actions, and that is basically everything that modifies your state. So these are the user events or the WebSocket connections. And then there are 2 quite similar concepts. So there are computed values. So these are basically our formulas, and they take some data and turn it into new values. So we have our coordinates, and we turn them into an SVG path describing our arrow. And there are also reactions, and they're very similar to computed values, except that they don't produce a value, they produce a side effect. And in computing, in the end, you always need a side effect somewhere, because in the end, you need either to make a network request or flush your rendering to the DOM, something like that. Those are reactions. So this is how we solved this problem at Mendix. We basically took the original model we described, the thing that minimally describes what lives in our application. We marked all the data in there as observable. We don't have any of that event listening stuff anymore. We don't need it. So and here is our minimal model. And then from there, we can create a component. And that component has a few interesting things. First, we marked our calculation for the SVG path as a computed property. And it basically tells MobX, this can be derived from the state. Do so whenever you please. And how that is derived from the state, that is up to MobX to figure out. You just provide the formula, which is still the same as it was in our previous slide. And there's another decorator. And if you don't like decorators or you aren't familiar with them, you can also use this in ES5 with normal functions. But personally, I like the declarative nature of decorators because they express what our intent is. And so this just signals MobX, this entire component, this entire rendering, can be derived completely from the state. Give me any state, and I can tell you how your component should look like. And so we can scrap all the component will mount stuff because we have a system in place that makes sure that our consistency cannot be violated. So and if we then look at the actions we had before, and you see that all the syncing stuff, all the manually imperative enforcing your laws is removed from here. So moving the entities is now just the matter of updating the facts that live in your state. And same for adding associations. And you don't have to think yourself anymore about, could this affect my rendering? Do I need to tell it to update? Because MobX has determined what the formulas are of your rendering. So roughly speaking, it knows that the association view component is a formula that just multiplies the SVG path with some constant HTML stuff. And the SVG path, in turn, takes the association parent and association child. And you don't have to tell it this. It will detect that itself from running your code. And it takes the coordinates of those entities. And it takes the amount of associations, because if one is added, it might need to update the rendering. And it takes their parent and child, because, well, those parent or childs might change in the future, and then they might become similar. But you don't have to figure this out yourself, that it all depends on it. It just will tell you that. And I can actually show you that this is behind it by using the DevTools of MobX, and I can click an association. And MobX has determined that all those values influence the rendering. And it's actually a tree, so there's an isRenderable property, which is, again, a formula in itself. So there's a tree of formulas building up the behavior of this component. So this is like the formula we just saw, but a bit more complicated because this implementation is more complicated. But so what it does is basically saving you thinking about which values might all invalidate your rendering and when you need to track that and such. So this has some benefits. So since we don't, the first and maybe the most important one is, since we don't have to enforce consistency in our application ourselves anymore, our actions become simple. So basically, again, a very scientific chart. When you add a new feature, you don't have to think about how this might be influenced by existing features already. So it means that your cost per feature remains a lot more constant. The second benefit is that our actions are now much more decoupled and much more scoped to the feature they are actually about. So we have an association, we have an entity. They both influence the anchors of our rendering. And there are actions which relate to either of those concepts. But those actions no longer need to care anymore what happens beyond the thing they directly affect. And they don't have to know about the existence of each other domains. So you might be wondering at this point, okay, that's all nice, but why all this effort to draw two boxes and an arrow? So let me take you through the picture, the bigger picture of what we are building at Mendix. So we build applications, and applications are described by a model. So we have a public SDK for that, and we have about 500 different concepts in our model. So we have entities and associations, and these are just two of those 500 concepts. So we have a public SDK for that, and this SDK is used by our teams. And this SDK just describes what our model is, and it also makes sure it's observable in its entirety. So then, of course, when you're building or using our application, you're manipulating an instance of such a model. So you're manipulating an actual application you're building. So there are editors for this. You just saw one, but there are many of them. And all those editors might edit different parts of the applications, or maybe several editors even edit the same part of the application, but from different views. And besides that, there are also third-party scripts made by third-party vendors, and they do analysis on these models, or they migrate existing applications into Mendix models. They can build all those kind of things. And we also have a rule engine. And that rule engine checks whether your application is valid. So for example, if you have two entities, they should have different names, because otherwise, well, you cannot generate a real database from it, because then the tables would collide. And so we have hundreds and hundreds and hundreds of these rules. And many of them are very complex. It's like a complete type checker. And the nice thing is that all those things are built by several teams, and even by separate compiers. And we actually have two applications. So we have a web-based modeler you just saw. We have also an existing desktop modeler. And some of the editors are used in both, and some of the editors are specific for one of those modelers. But the nice thing is that all those editors don't need to know about each other, and they are still in sync with each other. So if you get a random script from a partner, and we run it in our modeling environment, and that script starts to change arbitrary data, we still know that our editors will always be consistent, that they don't need to fire events like, now redraw everything for me, because we don't know what might have changed. Because we know that MobX takes care of that, so we can achieve a very high degree of decoupling, because everything can live independently. And so we are using those editors from different teams, and usually we don't even or hardly talk to these teams when we receive an editor from them. We just hang it in our application, we give it a model, and we know that it will work, and we don't have to communicate about each other. Well, we now introduce those 5 new actions and this 7 new reducers, so please take care of that. And we know they communicate through the model will be kept in sync, the rendering will always be consistent, so we don't care about what they do with model, what they render or what they change. So finally, I want to dive a bit into the rule engine. So you can imagine that a rule might look like this. Given a car and given a set of rules, whenever the speed of the car is higher than the allowed speed, then we should send it a fine. And when is a MobX function, and it takes two functions. The first is an expression, and whenever it returns true, the second function is started. And by just writing this, we know for sure that no matter under what circumstance the speed of the car changes, or under what circumstance the speed limit changes, but whenever this condition is violated, we know for sure that the driver will get a fine. So this is like the small picture. So real rules in our application more look like this. And they need a lot of data to check not just the car and the speed limit, but often they have to access huge amounts of data. And still, to run them, we can keep it very simple. So for example, we have a currently open document, like this document. And here in the bottom, there are 4 checks that are violated. And the only thing we need to do is that we take the library with all the consistency checks, put it and compute it, and we know that MobX will track whenever each of those rules need to be re-triggered because relevant data changes. We don't know what data is relevant for a rule. We cannot track it. We have hundreds of rules, and they use lots of data. But we know for sure that MobX will trigger the right rule at the right time because it has tracked which data is relevant for each rule. So that concept is called transparent reactive programming. And what it means for us is that consistency is guaranteed, regardless where data is consumed, and regardless where or when data is produced. So it allows us to move from the when should we run rules and how should we run them, to just describing what those rules are about. And you might have noticed that MobX code in generally looks quite simple. And for that reason, people often assume that MobX was designed to build simple applications. And I hope I have demonstrated sufficiently so far that we're not building something simple with it. But finally, another analogy. So suppose tonight you have 4 friends coming over for dinner. And so you have to prepare some meal for them. You can just order something, or go to a takeaway, or you can cook some nice meal yourself. Maybe the last one is a bit more work, but it also gives a bit more satisfaction. I don't know what you prefer. And actually, it really doesn't matter, right? Those are both very viable options. And the reason for that is that, well, 4 people isn't that much. Now, suppose that, like Moses, you're wandering in the desert and you have 1 million or 2 million, I don't know exactly, at least a lot of people with you. So, and you're in the desert, and you have to provide them food. So, now when you ask the same question, would you order a takeaway, or would you cook meals yourself? The answer becomes a lot simpler. Because cooking for this many people yourself won't scale. So again, you probably need a miracle. Something that is really easy to consume, like food falling from the sky. And maybe you don't exactly understand in its entirety how it works. It's a bit magical. But hey, that's what abstractions are for. So the thing is that simple solutions that are simple to consume, scale better. So that is basically what I wanted to tell you about real-world, scalable MobX usage. And while I was preparing this presentation, there was actually a nice tweet from a guy who wrote a few months back why he preferred Redux over MobX, because he likes it conceptually better and it's very clear to follow. And it is very nice. But he tweeted, even though I like Redux better for my own personal reasons, I see why using MobX makes more sense in a team setting. So he saw why it scales. So have minimal state and derive the rest. Make sure that you can have simple decoupled actions, because simplicity in the end adds up. So if you need miracles, check out the documentation. There's also a nice egghead introduction course. So check it out. Follow me on Twitter. And PS, we built everything in TypeScript. It's really awesome when you have big projects. It saved us tremendous amounts of time when doing refactorings and those kind of stuff. So watch Daniel's talk as well. It's right after this one. Thank you for listening.
How you doing? We love MobX. We work with it, and it's awesome. I have a question about the strict mode of MobX. So I started using the strict mode, and I was wondering if you can say a couple of words about it. And I was wondering at some point, do I really need the strict mode? Because kind of MobX takes care of things for me. So can you say a couple of words about that?
Yeah, sure. So strict mode enforces that you don't alter state in unexpected places. Basically, the reason why the feature was introduced is that people were conceptually scared. I can change data from anywhere. So is that what I want? So it got at a certain point the strict mode feature that makes sure that you are only changing state from inside an action. So it's kind of a feature that started by making people sure that they can control where their state is coming from. Their state changes are coming from. But in the end, personally, I hardly use strict mode myself, because I'm pretty sure I'm not trying to modify state at weird places, especially because I'm quite sure that my state is minimally defined. So even if I would change it in a weird place, then I still know that it will be dealt with. So it's a feature that is primarily meant to have people feel safe what they're doing. So it forces some constraints, but it doesn't really add some semantic benefit. Does that answer the question?
Yeah, I guess I was just kind of thinking, is there a benefit for the strict, like if I change a value directly and not through an action, like does MobX handle it?
Yeah, so actions themselves, they do have a lot of benefit. For example, they process changes automatically in a transaction for you. So it means if you make a lot of changes, it will only update all the derivations after you performed all your changes. So, and what strict mode does is it enforces you to use actions under all circumstances.